and good morning or good evening, everyone. So thank you all very much for coming. Today we are happy to have Maxime Fairon from the University of Glasgow, and he will tell us about the generalized Ruijsenaars-Schneider system from cyclic quivers.
Okay, so thank you first of all for you all to be there as early as 9:30 in the morning for you. For me, it's quite nice because I can drink my cup of tea, as I said. And so today, for my seminar, I will be talking about generalized Ruijsenaars-Schneider systems, and they are generalized in the sense that I will explain how the usual Ruijsenaars-Schneider system can be obtained from a very simple quiver, and all by using representation theory and changing the quiver. In fact, we can get something, well, quite interesting, I would say. So the plan for my talk is obviously to just give a quick recap about Calogero-Moser and Ruijsenaars-Schneider systems. So if you don't know what it is, don't worry, you can have a quick glance at that during the first part. Then I will spend quite a lot of time explaining how the spin Calogero-Moser systems can be obtained from cyclic quivers. Okay, and the idea there is that I will develop all the theory in some way to try to understand integrable systems using quivers. And then once this is done, we can just go to spin Ruijsenaars-Schneider systems and get new generalizations. Okay, so the Calogero-Moser system, so you may know it. So it is a system just describing n particles. Okay, so for me, these particles will be on the complex side, but they have obvious real versions, which in fact were originally introduced. And the idea is that the system is completely parameterized just by some position of the particles and their associated momenta. Okay, and the Hamiltonian, which describe the motion, is this one. Okay, so you have a kinetic term here, and then you have here a potential term, which up to some constant, this gamma squared, is inversely proportional to the distance between any two particles, and this distance is squared. So I'm showing that because from my point of view, I would say that the Hamiltonian is nice because just by looking at it, you can sort of understand a bit of the system. Okay, so you know that, for example, they may be repulsive or attractive systems depending on gamma. Okay, so for me, gamma is complex because I'm doing everything over the complex field. And what is really nice is also that you have several versions of this system. So I will only be talking about generalization of this rational system today, but obviously there are some trigonometric, hyperbolic, or elliptic versions of it where you change this potential. And they may also have some generalizations, but maybe not as many as what I want to explain in the rational case. Okay, so one kind of generalization that we can obtain is to add spins to this system. Okay, so what do I mean by spins? Well, here I'm adding for each I. Okay, so just remember that I is an index for a particle. Okay, and so for each I, we are adding a vector here, this AI alpha with d components. Okay, and so this is just really a vector attached to each particle. And conjugate to these AI alpha variables, we will have some variables that I denote BI alpha, so that we are looking at the moment at a space which has dimension 2n plus 2nd. So we have our original position of the particles, okay, then they have their momenta, then we have this spin attached to the particles and the corresponding conjugate variables. And what you can do with that is the following. You can now get a slight generalization of this Calogero-Moser Hamiltonian. Okay, and what is the difference is that here, if you look at the potential term, instead of having a potential term which is a constant, okay, so here there was a gamma squared on the previous slide. So instead of having a constant times 1 over the distance between the particles squared, now we have these couplings here that are coming and that depend on these extra degrees of freedoms, these spins that we have added. Okay, so for example, this Fij here that is appearing, basically you can see it as being obtained by pairing the vector of the A variables associated to the i's particles, and then you pair that with the vector of the B variables, okay, the conjugate variables attached to the J's particle. And what is really nice and was remarked by Gibbons and Erbson is that you can form an integrable system containing that Hamiltonian when you fix the Fii, okay, so when you take I equal J here, if you fix all these values to the same constant gamma and then identify some orbits, you can produce an integrable system. And let me just write down the equations of motion. They will not be really interesting, but just to somehow give a distinction between the Calogero-Moser and the Ruijsenaars-Schneider case. Here, what I just want to emphasize is that if you look at the equations of motion, you can kind of guess what the Hamiltonian function here. Okay, we will clearly not have that property for the Ruijsenaars-Schneider case, unfortunately. Okay, so I've introduced the non-spin and the spin Calogero-Moser Hamiltonians. I've told you that these things can be put inside an integrable system. Okay, and out of the blue, let me ask the question, is there a way to understand this integrable system graphically using representation theory only? Okay, so as I said, this question comes from nowhere. So let me ask something more. Even if we don't know how to answer this question yet, can we just have more than that? And can we also have generalizations using representation theory? And the answer will be yes, because we will be looking at cyclic quivers. Okay, so in the simplest non-spin case, really the idea of understanding things using the representation theory of quivers is due to Wilson, okay? And then in the spin case, there has been some work by Bielawski and Pitrigach for D equal 2 spins, okay? Then slightly more general by Tachela. And finally, using these cyclic quivers, this has been the work of Chalykh and Silantyev. And I will try to reinterpret all these works really using the quivers in the second part of this talk. But before I can arrive at that point, I just want to introduce what will be the third part of the talk. Okay, so trying to obtain the same question for Ruijsenaars-Schneider systems. Okay, and in that case, the thing that we kind of have to keep in mind is that instead of having the momenta, so the conjugate of the positions, which are the interesting variables, for some reason, what is more interesting is the exponential of these. And what is, well, I'm writing it in this really weird way. What I want to emphasize is that the Hamiltonian can be just obtained as being a sum of some new variables, these new I, so that this Hamiltonian really, if you look at it, you don't have any information about your system. Okay, but the point is that here, these new I variables, which are a bit obscure, they are basically a product of the exponential of your momenta. Okay, so these are these sigma I variables, and then a product depending on the position. Okay, what here is basically happening is that if you kind of want to understand generalization, what you have to do is go to equations of motion and just write them down. Okay, and so here the idea is that this new I will be what you obtain by as the time derivative of your position. Okay, and then when you derive them, you have this other thing here, which, well, obviously that doesn't look really nice, but this is the kind of equations of motion that we will be able to generalize. And in fact, this point of view of looking at the equations of motion, this is what is at the basis of the spin version of this Ruijsenaars-Schneider system, okay, that was introduced by Krzyzewski and Zabrodin. So again, let me just set the stage again. When we are talking about spin versions of a system, for me, what I really want to say is that we still have the position and the momenta of your particles in the background. But what you also have is some vector and the corresponding conjugate variables which are attached to each particle. Okay, so you get some phase space of dimension, okay, so 2n for the initial variables, and then you have 2n the extra variables. And the problem here with this spin Ruijsenaars-Schneider system is that everything is really cumbersome, because basically these are conjugate variables, these bi alpha, they do not appear explicitly in the equations of motion that I will write down, but there will be some other spin coordinates, so these ci alpha, that will show up. And in terms of those, you get this generalization of the Ruijsenaars-Schneider system with spin, okay, that was written down by Krichover and Zabrodin. And without going really into the detail, let me just say that what is kind of important to note is that if you look at your AI alpha, okay, so for fixed I, this is really the vector of spin variables attached to the ice particle. Okay, and these things will evolve over time using a sum depending on the other AG alpha. Okay, so alpha is fixed basically. And then there are some pairing occurring and some potential function. Okay, so I'm saying that this is kind of a potential function because it just depends on the position. And then there is a similar thing happening for the C variables. But here my point is really to say that if you just look at these equations of motion, well, you don't have much information. Okay, so as I said, we can't say much from these Hamiltonian, but let me still ask the question, is there a way to understand these integrable systems graphically using representation theory? And can we find generalizations? And the answer will again be yes. And we will be looking at cyclic quivers, and this will be the last part of this talk. So let me maybe stop here for a second and just ask you if you have any question at the moment. So if this is all right, I will just continue then and move on to the spin Calogero-Moser systems. Okay, well, there are several such systems because we will have generalization from cyclic quivers. Okay, so first, let us try to reinterpret the usual Calogero-Moser system using a quiver. Okay, so a quiver for me, as you see on the left-hand side, and if you don't know it, it's just a directed graph, okay? So you have some vertices. These are these black dots with a name in them, and then you have some arrows. And what you can do with this quiver is form the corresponding path algebra. Okay, so the path algebra of this quiver that I'm denoting Q1 bar, the path algebra will be denoted CQ1 bar. And basically, this is just the algebra generated by all the paths that you can form with these different arrows. So for example, you can have the path where you go, I don't know, k times through x. So you will write that x to the k. You could have the path vx, okay, so going through v then x, and so on and so forth. Here, let me maybe just emphasize that I'm using a convention that is not the usual one for representation theorists, and I'm looking at how I'm writing the path from left to right. Okay, so really for me, Vx just means going through V, then going through X. So assuming that you're happy with this this algebra, well, what we can do is just look at representations of it for some particular dimension vector. So that's what I mean by this n1. What I mean is that I will attach Cn at 0, and I will attach C at this infinity vertex. So it means that in terms of matrices, when I'm going to representation, this matrix X will go from Cn to Cn. Okay, so it will be a n times n matrix. The same will be true for the matrix Y, which is also a loop based at 0, so it will also go from Cn to Cn. And then, because of my weird convention of writing paths, V, which goes from C to Cn, okay, I will write things in the opposite direction, so I will say that V will be a 1 times n matrix. And W, which is between Cn and C, I will say that it will be n times 1. Okay, so I'm just in some way looking at the dimension in the opposite order if this is confusing you. But apart from that, everything is really basic here. So this is a big space that we can form from this from the representation of this quiver, okay? And what's happening is that on that space, because I'm attaching the vector space Cn at 0, I can change bases, okay? So I have a GL and C action on the space. And it happens that this space for that particular action has a moment map. So this is what I'm writing here by this commutator of x and y minus WV. This is a moment map for this GLN action. And fixing this moment map to some value and then looking at the corresponding orbit space, you get a smooth manifold, which is the nth Calogero-Moser space. Okay, so here, let me just say that I'm taking the GIT quotient because a priori, you don't know that the space will be a smooth manifold, but it turns out that here, the situation is very nice. This is the result of Wilson. And so you just get a manifold. This is just an orbit space. So what I want to emphasize here is that to get this nth Calogero-Moser space, okay, and I will explain on the next slide why it is called like that. To get this space, basically what we do is just we perform a Hamiltonian reduction of some representation space associated to a quiver. This is the general idea that I will generalize later on. But before doing that, let me maybe just say that with respect to the Poisson structure for which we have a moment map for this GLN action, the function which are obtained by taking different powers of y and then taking the trace of that, such functions are Poisson commuting. And what I just want you to visualize is that these functions, in some way, you can just think of them as going through the loop on the quiver yk times. Okay, so this trace yk, in some way, this is just going through little yk times. So this is for a first connection to quivers. Now let me just briefly explain why this is called the Calogero-Moser space. Okay, so the idea is that on a dense subset of this space obtained by Hamiltonian reduction, you can put x in diagonal form with distinct eigenvalues, and you can assume that the covector v is just made of a bunch of ones. Okay. And this basically is fixing your gauge action up to a residual finite action by permutation. But forgetting about that, what's happening is that you can solve this moment map equation, this commutator of x and y minus WV equal the identity. And so by going to the diagonal entries of this identity, you get that W is just a vector form of -1. And then your Y matrix has a really nice form because basically its diagonal entries are free. So we will call them PJ. And then the off-diagonal entries have this nice form that are in 1 over the difference between Qi and Qj. So the difference between the eigenvalues of the X matrix. And in terms of, oh, yes.
Can I have a question? So, yeah. So this is more or less equivalent to this old construction of Kazhdan constant Steinberg.
Yes, the only difference
for the cotangent bundle of the GLN.
Yes, here it's just a complex case. That's the only difference. Yes, yes. Yeah. So yes, really, this is the GLNC version of that. So what here I just want to emphasize is that to make the connection, if you don't know it, when you take the trace of this matrix Y squared, okay, and then take half of it, you basically get back your Hamiltonian of the Calogero-Moser space, of the Calogero-Moser system with coupling equal to 1. But basically, up to changing where you do the Hamiltonian reduction, this coupling, you can get it to be any non-zero complex number. So this is where this name comes from. So now let me try to ask this question. How much information on the space, okay, on this space which is related to the Calogero-Moser system, how much information can we push onto the quiver? So again, just by looking at it, as I said, in some way, we can think of the parse algebra of the quiver as being really giving us the representation space, okay? So up to knowing which vector spaces we will be attaching at 0 and infinity. Then the matrices on that space, on that curly Mn1 space, well, these matrices are just representing the arrows, okay? So we can think of them as being the arrows. And then the moment map here can just be realized as being the matrix representing this element, this commutator of x and y minus wv in terms of the elements on the parse algebra. And finally, as I said, the elements which form the integrable system, we can just think of them as being these loops y to the k that we are taking. So just by looking at the quiver, we already know some information, but a big question is to understand what about the Poisson structure? Can we also realize it at the level of the quiver? Okay, so I didn't write it on the previous slide, but this is basically the two Poisson brackets that generate the Poisson structure on this curly Mn1. And the question is, can we realize that at the level of the quiver directly? And the answer is yes, using double brackets. So I guess you may know about double brackets because, for example, Semyon has worked with that quite a lot. But if you don't, let me...
It's better to explain anyway to the audience.
Yeah, exactly. But anyway, I really like to talk about that topic, so I will redefine this notion again here. Okay, so this notion of double bracket is due to Van den Bergh. Okay, and basically it's as we will see, this is really a non-commutative version of a Poisson bracket. I will explain that precisely in a couple of slides. Okay, so just to set the stage, we work over a finitely generated associative algebra over C. So I'm just working over C because that's how I think. Okay, so all tensor products are over C. And I will use this strong version of Swidger's notation, okay, that whenever I take an element in the tensor product of A with itself, so an element D, I will just write it as being D prime tensor D second. Okay, so the idea is that all the operations that I will do are linear, so I don't really care about writing the sums explicitly. And some other notation, this tau1, 2, which is just swapping the two elements in the tensor product, and then there is an obvious multiplication of this algebra. So given all these things, we can define the double bracket. Okay, so what is it? So let me maybe say the first thing that is different from into my usual Poisson bracket is that here, as you see, the operation will be valued in A tensor A. Okay, so it's not something that takes two arguments in an algebra and pops you again an argument in this algebra. It gives you something in the tensor product of this algebra with itself, and it satisfies some properties. Okay, so first here we have a non-commutative version of antisymmetry. Okay, so a usual antisymmetry, what you would expect is just that when you swap the two elements in your bracket, you get a minus sign. So here, because I have to recall that we are working in the tensor product of A with itself, what we will do is not only put a minus sign when we swap the two arguments, but we also have to swap the two elements in the tensor product of the element that we obtain in A tensor A. Okay, so this is what this tau1, 2 is doing. It's just swapping the elements. And then we have here two derivations rules. Okay, so let me maybe explicitly explain what is this derivation rule with respect to the second argument. Okay, so what it's giving you is that when you take this derivation rule, the element B, which is on the left in the second argument, will be multiplying on the left the first element of the tensor product of the double bracket between the other two elements, okay? And then the C, which is appearing second in this argument, will be multiplying on the right the second argument in the tensor product of the double bracket of A with B. So it's more or less a usual derivation rule. It's just that because your double bracket is valued in A tensor A, you have to be careful on which side you will be multiplying. And in particular, due to the cyclic antisymmetry, this rule number 2 will give you, or you have a Leibniz rule in the first argument, and it will be basically multiplying on the left or on the right the other element of the tensor product. So what I did so far, I will explain that exactly in a couple of slides, but what I did so far is give you a non-commutative version of an operation which is antisymmetric and a biderivation. So to get a Poisson bracket, usually you would expect also to have a Jacobi identity which is satisfied. So let's go to the non-commutative version of that. Okay, so here's what you do. So obviously your Jacobi identity, usually you would expect to take 3 elements in your algebra and do something with them and get 0. Okay, so this is basically what's happening here. So you take 3 elements, A, B, C, and then what you do, you first compute a double bracket between 2 elements. Okay, so for example, I can compute the double bracket of B and C, which, remembering my notation, I'm writing as being the double bracket of BC prime tensor double bracket of BC second. So I have 2 elements in the tensor product. And so if I want again to apply a double bracket on that, well, you have to choose on which element in the tensor product you have to apply it. And basically the rule is just to apply a double bracket with the first element in this tensor product. So I will not go into the detail of that because we will not really need it, and it may be difficult to digest at first sight. But the point is that we can define such an operation, and we will say that our double bracket is Poisson if this operation just vanishes. So again, this is really like your usual Jacobi identity, but in these non-commutative settings that I want to introduce. And before giving you the connection with the usual commutative case, let me just give you 2 examples. So the first one is nice because, okay, so it's just a double bracket on the free algebra in 1 element. And what is nice is that you can see that your double bracket of an element with itself is not necessarily 0, okay? Because of the cyclic antisymmetry, you don't necessarily have that the double bracket of X with itself is 0, but it can have this particular form here. Okay, and the second example that I want to give, which may intuitively be a bit better to understand, because it's basically a kind of a symplectic double bracket. Okay, so well, this will be easy to understand in one side, but let me just say that basically you have 2 generators, X and Y. The double bracket of each element with itself is 0, but these 2 elements, when you take the double bracket between them, it gives you just the identity. Okay, because remember the double bracket is with value in A tensor A. Okay, so 1 tensor 1 is just the identity element, your unit in A tensor A. Great. So now is the really nice result, this proposition of van den Bergh. So before I can really state it, just let me remind you that notation, okay, that Strong-Reader's notation, that whenever I compute the double bracket of something A with B, okay, I can write it as being the double bracket primed and so the double bracket second. Okay, so this is just a notation. And what I also need to introduce as notation is that, well, it's just some matrix notation on representation spaces. Okay, so let me denote by this rep an, just your moduli space of all n-dimensional representation of an algebra A, okay? And on that representation space, you can basically form a matrix that I'm writing Aij, which is basically the matrix which is returning you the element representing the element A in each representation. Okay, and so in particular, I can look at this Aij as being a function on this representation space, which returns the Ig entry of the matrix representing the element A. This is all we have to understand these symbols here. And if you're happy with that notation, then we can go to the proposition of van den Bergh, which is as follows. If we have an algebra A which has a double bracket, then the coordinate ring of the representation space of A of some fixed dimension n this coordinate ring will have a unique antisymmetric biderivation that I'm writing this bracket P, satisfying some rule. Okay, so let me explain that rule later on. Before that, let me just say that if furthermore this double bracket is in fact Poisson, then this antisymmetric biderivation is in fact Poisson bracket. So this is why really I'm saying that this notion of double Poisson bracket is a non-commutative version of a usual Poisson bracket, because when you go to representation spaces, you get back your usual notion. Okay, so what is the rule to define this operation on the representation space? Well, it is as follows. So if I want to evaluate this bracket now on representation space between the ij entry of the matrix representing the element A and the KL entry of the matrix representing the element B, well, what you have to do is the following. Maybe I should write it, maybe easier. Okay, so I can annotate. Okay, so to really understand what you have to do here, the first thing to remember is that you can compute the double bracket of A and B. Okay, so this is what I'm writing here. Okay, and because of my notation, this double bracket, I can just write it as being double bracket prime tensor, double bracket second. Okay, so what you can do then to go back to representation spaces is look at the matrix representing each of these two elements in the tensor product, okay? And what you can do is and what you will do basically is the following. So you look at the matrix representing the first element in this double bracket, and you take the kj entry of this, okay? So why kj basically? Because you take the first entry of the second element, this b that you want to evaluate. So you take the first index, and then you take the second index of the first argument here. And then you take the remaining two indices, and you look at the corresponding matrix element in the matrix representing the second element in the of the double bracket in this tensor product. So this may seem a bit of a cumbersome rule at first sight, but the point is that when you deal with computation, for example, or when you want to understand anything, this is really convenient. So let me maybe stop here and ask you if you are happy with this. So I will not use that much, but I think it's really nice if you can just keep one thing from this talk, is just to remember this proposition of Van den Bergh that a double Poisson bracket is a non-commutative version of a Poisson bracket in the sense of that proposition, because I think it's really a brilliant result. Okay. So just to give you this example, so I was telling you that this free algebra on two generators, which was such that the pairing, okay, so the double bracket of the two generators was the unit. Okay, I was telling you that this was like your a symplectic double Poisson bracket. And why I was telling that is that because when you go on representation spaces, okay, so if you look at n-dimensional representation of this algebra, well, here X will be an element from Cn to Cn, so it's just a n times n matrix. The same for Y. So the coordinate ring of this is just really just a bunch of two n times n matrices. And if now you use this particular rule to understand from the double brackets how to get the corresponding usual Poisson brackets, then you see that you get your canonical Poisson bracket on T star GLN, okay, which you know to be symplectic. Okay, so for me, for example, this double bracket is really nice because it's very easy to write down. And okay, obviously the geometric one, the one on T star GN, it's not that bad to write down, but it's even more concise to write the double bracket. So all this digression for one thing, well, just because Van den Bergh explained that given any quiver, you can associate to it double Poisson bracket. So how is the deconstruction working? Well, okay, so just for notation, if I fix a quiver Q, okay, I denote by Q bar the double, okay? So the double just means that for any arrow in the initial quiver, if the arrow, for example, is going from a vertex T to a vertex H, then I'm adding in the double an arrow going in the opposite direction, okay? That I will denote by A star because I want to remember that this is paired to the original one, okay? And so the proposition of Vandenberg is the following. So I may not really go into the detail, but basically it's telling you that there is a double Poisson bracket on the path algebra of the double of any quiver. And this double Poisson bracket is such that, well, it's non-zero whenever you take an element, an arrow in the original quiver with the corresponding double. Okay. So here, this notation, these idempotents, if you know them basically, well, if you know a bit of quivers and path algebra, here I'm taking the idempotent, which is based at the vertex, which is the head of A, and here the idempotent, which is based at the tail of A. But basically, if you don't know really what this means, it's just that here we are taking the element 1 tensor 1, but because there is an idempotent decomposition in the algebra, this is how 1 tensor 1 will look like when restricted onto these two elements. That's really the idea. And then the second rule is just to say that whenever you take any two arrows in the double quiver which are unrelated, the double bracket is 0. And you get a double Poisson bracket. So what I'm also adding here as a small note is that you have more than that. In fact, Vandenberg explains that there is a notion of a non-commutative moment map. And what this means basically is it's really in the same philosophy as we had earlier. Okay, so a double Poisson bracket was giving on a representation spaces a usual Poisson bracket, and in particular the moment map depending on the moment map depending on the double Poisson bracket will give you a usual moment map associated to the corresponding Poisson bracket. So, well, this moment map we will need it to perform Hamiltonian reduction and get this relation to the integrable systems later on. But before going there, let's just explain how we go to representation spaces when we are given a quiver. Well, because there are some vertices, okay, so here I is the index set of my vertices, the idea is that we will attach some vector space at each vertex, okay, so I fix some dimension alpha S going to the vertex S, for example, and then I will see the arrows as being matrices between these vector spaces in the same way as I was doing earlier. And then using this proposition of Vandenberg, but now using the fact that there is a decomposition with idempotence that I don't want to go into details, the idea is that the representation space of this path algebra is a Poisson structure, okay, given not by the proposition that you see now, but the previous one. But the fact that we have a moment map tells us that we can perform Hamiltonian reduction. And in fact, you get the usual notion of quiver varieties when you do that Hamiltonian reduction. So in some way, these double Poisson bracket associated to quivers by Vandenberg, they are really just a realization of the Poisson structure of quiver varieties at the level of quivers directly. So let me maybe stop for a second if someone has a question. So if not, let me continue then. And now be back to the case of trying to understand what can go, what can be generalized with integrable systems. Okay, so as you see, in the case of the Calogero-Moser system, we had this really nice quiver, this Q1 bar that I was telling you about. And the idea is that, in fact, this quiver is the double of the quiver here Q1, okay, where with my previous notation, Y was now the double of the original loop X, and this W was the double of the original arrow V. And by this formalism of Vandenberg, you have a double Poisson bracket and a moment map, and they really give you back what you want, okay? Because when you take the particular dimensions that I was telling you. So here I'm attaching Cn at 0 and C at infinity. Then what's happening is that the arrows have the correct size. Well, the matrices, sorry, representing the arrows have the size that I was claiming they have. But more importantly, from the double Poisson bracket, you can get the Poisson structure, which is used to perform this Hamiltonian reduction to go to the Calogero-Moser space. So, well, this is an exercise to derive that, but yeah, I may not have much time to do that, so let's skip it. So, what is, I don't remember why I wrote this slide, but yeah, okay, yeah, maybe it's really to give you again a hint of what's this correspondence between quivers and spaces on which there is an integrable system. Okay, because if we have this free first rule that I was telling you about, okay, so we fix some dimension and then we can realize the Poisson structure at the level of the quiver, and in fact also the moment map. What's then happening is that when we select, for example, the moment map to be put to some values, or here just the identity, and then we look at the corresponding orbit space, okay, we have performed Hamiltonian reduction when we do that, and we get this space, this Calogero-Moser space of Wilson. So the idea is now to just try to generalize this last red step for other quivers, okay? Just trying again to perform Hamiltonian reduction, but with more general quivers. So this is this idea of, I would say, really the first one to have explained that, though in all these references, the notion of double bracket is not really used, but the first one to try to go to the spin version of the Calogero-Moser system using quivers were Bielawski and Pitrigacz. Then Tachela did that in more or less full generalities. But then the most important point of view for me is the work of Chalykh and Silantyev, because they had generalization with cyclic quivers, which will be interesting for us. And once you understand the story with just an extended one-room quiver, it will be easy to understand everything. Okay, so what are we doing now? Well, we look at this initial quiver where instead of having just one arrow from infinity to 0, we take d of them. Okay, so this d will be the number of spin variables that we are adding. This will be the relation to the system that we have. And then we double this quiver by adding these dotted lines. Okay, so there is the y, and then each w alpha will be the double of the corresponding v alpha with the same index. And then here, the idea is that without even thinking, let's just reproduce what has worked in the case of the non-spin case, okay? So we take dimension vectors such that Cn is at 0, C is at infinity, and then we perform Hamiltonian reduction at the identity. Okay, so as previously, your x and y are just n times n matrices. These, all the v alpha now represent the corresponding arrows, little v alpha. Okay, and these things, I see them as being covectors, and then the matrix is w alpha representing the little w alpha are now vectors. And now the idea is that when you perform the Hamiltonian reduction, you look at this particular space here, where instead of just having your commutator of x and y minus wv is the identity, now you take a sum of a bunch of these w alpha, v alpha that you subtract. And the key thing is that on this space, you can find coordinates such that, again, the trace of y squared, so again, just think of this as being the loop y on which you are going twice. This thing is in particular the Hamiltonian of the Calogero-Moser system with spins. Okay, and the number of spins is the number of extra rows that you have added. So there is obviously a bit of work there, but intuitively, when you just think at the level of the quiver, everything seems quite nice. What I just want to emphasize is that, okay, so maybe let's go here again. So in the case d equal 1, the non-spin case, we knew from the work of Wilson that to get an integrable system, we just go through the, we just take trace of the matrices representing going k times through the loop y, okay? The only thing is that if you just look at this trace of y to the k, again, on this extended space, you cannot form an integrable system because you obviously don't have many functions that are Poisson commuting. So the idea to get more Poisson commuting function in that case is just, again, just look at the quiver. And what's the simplest thing that you can do except going through the loop y k times or l times? Well, you can decide to first begin at infinity, take one of these v alpha arrow to go up, then go l times through your loop, and then go back to infinity using one of these double arrows. And what's happening, and you can compute all of that just with the double bracket, is that all these functions, they Poisson commute with the trace of yk. So here you have a really good way to maybe think about getting an integrable system. And the idea is that by just looking a bit carefully at these extra functions, you can explicitly get them by just noticing that if you go back with the same index as you were going up, okay, so if you go with v alpha, you come back with w alpha, then all such function Poisson commute. And you can, in some way, understand everything at the level of the quiver. And basically, you can prove Liouville integrability up to a few lines, but it's not too difficult to do. Okay, so my idea is that if you understand that, then you could go to the more general setting of looking at a cyclic quiver. Okay, so what's happening here? Let's just decompose this image. So you first begin with a cyclic quiver. So this is just, sorry. So this is basically the quiver at on the outer part of this diagram. Okay, so you just have a m vertices going from 0 to m minus 1. And between any two vertices, for example, here between 0 and 1, you have the arrow x0. Then between 1 and 2, you have x1, and so on and so forth. So this gives you a quiver. And the idea is that if you think of that cyclic quiver as generalizing your loop x that you had, what we were doing previously to get integrable system, what we were doing was to add an extra vertex, this infinity here in the middle, and then add a bunch of arrows from this new vertex to the other vertex that was there, the 0 vertex. So here, because we have a cyclic quiver, we have really several other vertices to which we can add arrows from the new infinity vertex. Okay, so the idea is that here you can just add ds of them, for example, from infinity to s. ds is any number that you want. Really. So this gives you your original quiver, then you double everything, meaning that you just add an arrow in the opposite direction to all the previous ones. And then what's happening is that the thing generalizing this y loop from which we were constructing, for example, the Calogero-Moser system, here is just this red path going counterclockwise on the cyclic quiver, okay? So this is what I denote by y bullet, this going from 0 to with y from 0 to m minus 1 using y to the m minus 1 and so on and so forth. And what's happening is that when you will go to representation spaces, just by knowing the double bracket, you know that the trace of any power of the matrix representing this path y bullet with any other such function, these things will be Poisson commuting. Okay, and you know that just by knowing the double bracket, which is given to you by Vandenberg. So there is a huge chance in some way that you could get an integrable system in the end. And okay, I may not have much time, but here is a slide with explicitly, for example, the GLN C times M action. Okay, so you have a copy of GLN acting on at each vertex in some way. So the idea is that going from this quiver to representation spaces, basically what we do, we attach Cn at all the vertices on the cyclic quiver. And again, we just attach C at infinity. Okay, so you have an action that you can write on. You have a moment map, again, by just the result of Vandenberg. And the idea is that you can just reduce, perform Hamiltonian reduction, and get a generalization of that Calogero-Moser space. The point is that, and this was first so demonstrated by Chalykh and Silantyev, that you can build an integrable system. Okay, and what in fact they did was to realize that this integrable system was related to the matrix KP hierarchy. But in fact, there is, because my emphasis here is to try to understand everything just at the level of the quiver, I have something a bit more, well, a bit easier to understand that. And the idea to build an integrable system I'm claiming is just the following. So as some function of interest, you just take this y bullet, okay? So y bullet, remember, it's just going one time through the cyclic quiver counterclockwise. So you can do that k times, then look at the matrices representing that and take the trace. Such things are Poisson commuting by just looking at the Poisson bracket given by Vandenberg. But what you can do if you want more functions that are Poisson commuting and to build an integrable system is just a trick of starting at the new extra vertex, this infinity, go to one of the vertices S with one of the added arrows that you have. So for example, this VS alpha. Then you go a bunch of times through your cyclic quiver. So this is this y bullet K. And then you come back to infinity using the exact same, well, the exact double of the arrows from which you were starting from infinity. Okay, so here it's really important that the two indices are the same in order to build an integrable system. So from this point of view, it's quite nice to visualize the integrable system at the level of the quiver. But what's in fact happening is that you can show that the function trace of y bullet to the k, for any fixed k, this function is in fact maximally superintegrable. So this is some work in progress with Tamás Gerber from the University of Leeds, which will shortly be available, I guess. But it's really natural to expect that, okay? Because, for example, in the case of the usual Calogero-Moser system, you know that it's maximally superintegrable. This was a work of Wojciechowski. Then with spins, it's really easy to get that generalization. So now getting that extra generalization with cyclic quivers is quite expected, I would say, but it's still very nice to derive. Okay, so let me maybe stop here and ask you if you have any question about this big bunch of theory, and then I will quickly go about the Ruijsenaars-Schneider version because it's quite easy when you understand all of that.
Maxime, I'm just curious if you know our paper with Semyon Artamonov.
Yes, I saw that. Yes, so it's maybe we can talk about that in 5 minutes when I'm going to the Ruijsenaars-Schneider case. Because so if I'm correct, you deal with Ruijsenaars-Schneider systems, right?
Yes.
Well,
yes. We deal with trigonometric case, so that's
yeah.
It's both Ruijsenaars-Schneider and spin Calogero-Moser, since at the level of relativistic systems, they are the same. They're just different by an automorphism.
Oh, right. Yes. So, okay. So here, maybe let me say that everything that I'm talking about is for the rational, some rational versions. Okay. But I think that the connection maybe to what you did would be that, okay, so let me maybe annotate.
My understanding is that what you did can be rephrased in the usual Poisson terminology, but it's a flat version of what we did in the neighborhood of the identity. For us, the moduli space is the moduli space of flat connections, so they are natural if you want, coordinates, the holonomies around cycles, and they are group valued. So if you consider the neighborhood of the identity, then it will be all flat.
Yes.
And I think this is exactly what you were talking about. In case when you have a torus with n punctures.
Yes. I can't say it for sure, but yeah, I think I see the idea. Yes. I would say that this is at least very similar, so there should be a connection. Yes.
Yeah. Oh, but it's nice. But you see, when you do it through the modular space, the advantage is that you can do it for any simple Lie groups.
Mhm.
The disadvantage
Yes.
is that you don't have explicit coordinates.
Yeah, so here maybe that's maybe the difference is that I can build explicitly very nice coordinates, but I'm really in the GL and C case. Okay, so I, as far as I know at the moment with this formalism of double brackets, it cannot be changed. Yes.
I'm just wondering if the same can be done, at this group level, not at the flat level as you're doing, sort of for Lie algebras, but at the group level with the cluster coordinates on groups.
So yeah, I don't really. Let me maybe explain the trigonometric Ruijsenaars-Schneider version, and you could see a connection with that. Yeah. So okay, yeah, let me continue, and then we can
No, it's
discuss
just,
again.
okay.
Yeah.
It was just a question.
Yes. But yeah.
Please go ahead.
Yeah. Okay. So to go to this spin Ruijsenaars-Schneider system, what we do is the following. Okay, so yeah, let me just recap what we did. Okay, so what we were doing is just for some quiver that for some reason is nice enough, we fix a space of representation of it. And we know that on this representation space, there is a Poisson bracket and a moment map because of Vandenberg's theory of double Poisson brackets. And then we just perform Hamiltonian reduction and we construct an integrable system by being smart or by basically just looking at the quiver. Okay. So the idea is that all of that can be extended to the case of quasi-Poisson bracket. Okay, so I guess some of you know what is a quasi-Poisson bracket, but if you don't know it, basically the idea is that geometrically, you can have spaces that almost have a Poisson bracket, but Jacobi identity is not satisfied. Okay, but the failure of Jacobi identity is governed by your Lie group action. Okay, so that when you go to orbit spaces, you get back your usual Jacobi identity, and everything is in some way very nice. Okay, so there is a quasi version of Hamiltonian reduction. This is what is usually called quasi-Hamiltonian reduction, obviously. But the point is that, and this is really why this work of Vandenberg is really nice, is that introduce double quasi-Poisson brackets, okay, as a way to define at the level of quivers, okay, a structure such that whenever you go to representation spaces of these quivers, up to discarding some hypersurfaces, which basically just means that you want to invert some matrices, but up to doing that, you obtain a space which has this geometric version of a quasi-Poisson bracket. And so that there you can perform quasi-Hamiltonian reduction and again, try to construct an integrable system. So yes, I think I will really quickly sketch everything because I'm out of time. But let me maybe say that the idea is the first thing that I did with Chalykh, who was my supervisor when we did that, is to just try again to use this quiver that worked in the non-spin Calogero-Moser system. And the idea is that if you use this double quasi-Poisson bracket of Vandenberg, you can, after performing your quasi-Hamiltonian reduction, obtain such a space. Okay, and on this space, you can realize your Ruijsenaars-Schneider Hamiltonian as being the trace of these Z matrices. So these Z matrices are like the double of these X. Okay, and I think here the connection with the moduli space of flat connection for a torus is more or less visible because here you have your group valued moment map. And
yes, that's exactly the torus with the rank 1 conjugation orbit at the function.
Yeah. Mm-hmm. Yeah. And so here, what is just new with that work of Oleg is just to have this double bracket entering the picture, but otherwise it's well known that you can find coordinates such that you get your usual Ruijsenaars-Schneider Hamiltonian. And yeah, let me not talk too much about that. What is more interesting, and we did with Oleg, is just do the following. Well, we know that this quiver in this double Poisson bracket case gives you, after playing a bit, the spin Calogero-Moser system. So you can ask the question, well, what happens with the quasi-Poisson setting? So here what's happening is that well, here you again have this group valued moment map of the elements representing the arrows X and Z, but now you multiply this by a bunch of rank identity plus rank 1 matrices. Okay. And the idea is that when you do that, and in fact rearrange this product, well, you just multiply it to put it on the right hand side and rearrange it to be a product, a product of n times d times a d times n matrix, you can realize your matrix Z. Okay, so the matrix representing this loop in suitable coordinate as being the spin trigonometric Ruijsenaars-Schneider lax matrix. And I don't really have time to explain that, but well, okay, so this is this first generalization that we can discuss later on. But yeah, let me maybe just say that understanding, so using this double bracket to understand what was the quasi-Poisson bracket on the big space before performing this quasi-Hamiltonian reduction and getting the reduced Poisson structure from which we could write the Poisson bracket on local coordinates was really important, because basically determining this local Poisson bracket was an open problem of Arytionov and Frolov that they stated in the 90s. And what is really nice is that here, having this whole story of quivers entering the picture, we could compute everything quite nicely. But okay, so the idea, and again, I don't want to explain that, is that you can form an integrable system containing these functions, so these trace of z to the n. Okay, so it requires a bit of work, and I don't want to explain that, but you can form the integrable system. But what's a bit more interesting is that, in fact, you have generalization for cyclic quivers, okay? Where, again, you just look at the quiver that worked in the usual double Poisson bracket case and go to the quasi-Poisson setting and just try to mess things up to get something. And what can happen is the following. So for suitable dimension vector, so by that I mean that I'm taking the same dimension n at all the vertices in that quiver, but at this new extra infinity arrow, I'm just putting c. Okay, so for such a dimension vector and generic parameters for your quasi-Hamiltonian reduction, you can build an integrable system containing these functions, which are basically meaning the function representing going through the quiver counterclockwise. Okay, so it's quite nice to visualize. But what you can also do, okay, yes, maybe let me say that for one framing arrow, this was already in our paper with Oleg from 2017, but the general case is in my PhD thesis, and as anything, I'm really expecting to write that down as an article one day. But yeah, let's see how it goes, hopefully this winter. Okay, but what's really nice, and I will finish on that because I'm quite over time now, is that you can, in fact, find local coordinates such that when you look at the corresponding equations of motion of a particular Hamiltonian, which really looks like your Hamiltonian for the spin Ruijsenaars-Schneider system of Krichever and Zabrodin. Okay, so your Hamiltonian looks really similar, and then the equations of motion look again really similar for some part of the coordinates. It's just that because you have in some way more arrows, okay, and so there is more information going on, then things are a bit more complicated. But apart from that, it's, from my point of view, a very nice generalization. Okay, and so on these bad-looking equations, let me thank you for your attention, and please ask questions if you have any.
Thank you.
Thank you.
So, any questions so far? Okay, then I'll probably. Oh,
I ask my questions, but I can ask much more. Unfortunately, I have to teach at 11.
Yeah.
But maybe we can have a Zoom conversation about this. I mean, yeah. I just want to. I hear about this non-commutative Poisson brackets, double brackets from Semyon a lot, but yes. I'm still not convinced that what you can do with these brackets that you cannot do with the Poisson brackets.
Oh, that's nothing. It's just you'll do it 100 times easier and faster.
Yeah, I think yes, the idea it's like in the Poisson case, why would you use an R matrix instead of writing down your Poisson bracket in terms of coordinates, just because it's easier and you?
No.
Yeah.
No, because it reflects certain structure that that you cannot express in coordinates. It's a functorial structure.
Yeah. So it's well, in a sense, it's all hidden in the way people write this explicitly in terms of matrices. Really, it's just not manifest there. So
Okay.
it's but no, you're right. Those are universal formulas for all n. That's mainly the key point. But if you look back and you know how people wrote this Poisson brackets, they also written universally for all n. It's not that.
All right. Well, it's not a criticism. It's just I want to understand it.
Yeah. Well, yeah. In my opinion, at the moment, it's really so much faster to play with those double brackets to do my computations. And well, I don't know if there is really a way to explain the structure that they have, but I would say it's like any kind of mathematical structure. At some point, you stare so much at them that you begin to understand a bit what's going on. But yeah, at the moment, I couldn't really say what is extremely nice about them, except
but it does simplify things
a lot. Yes, a lot. Mm-hmm.
All right. Well, thank you. I unfortunately I have to teach.
Well, yeah, no problem. Your students first, obviously.
I'm leaving, but
yeah. Well, thank you for being there.
Thank you.